Let's do some more work on our game that we started in the last video. We left the game basically running for input and output, although we're missing a random number generator. We're missing a count of how many times it took to guess the number, and we're missing the high-low hint. But for now, let's just check how the program runs. Random number generator currently returns 0, so if we put in any other number, it's going to say wrong guess and give us a chance to guess again. Let's go for a hex number, and that works. And let's try 00. So the basic logic's here. We've got it working. It detects the right number. Input and output works. Screen driver's working. Let's play with the program and see what steps we want to take next. Let's start with the most fun part, which is the random number generator. And there's a whole science, I'm sure, behind random number generation, but we have an easy way to do that with this hardware. And you can't just make a random number counter that's synchronous to the program, but randomness comes in by the menuing and the fact that the user's selecting when to hit enter. So if we read one of the timers that we have, preferably a fast timer on the card, and return back the bottom byte out of that timer, we should be able to use that as a random number. Now, if we read that same timer from when the card is reset, we pretty much get back the same number or close to it every time. So the fact that we're sitting here waiting on input from someone to type their guess lets that number reach a random value, and the chance of always typing in the number at the same amount of nanoseconds or 20s of nanoseconds would be a challenge. So what timers do we have available? Let's take a look. For that, we'll take a quick look at the memory map, which has the description of the individual peripherals inside of the card. And we'll see what timers we have. We have quite a few timers built into here. And we're going to go to the timer section and see what we have. Let's see, keyboard, UART, push buttons, and timers. And we have an elapsed time counter at 3800 hex. So if we read that time counter, that should give us back a 50 megahertz tick, so every 20 nanoseconds it increments. And it's a pretty big number, so we can read the whole thing and use that to have a random number. It's good enough for what we're doing, and I think it should work just fine. So let's add that code to that location to our code. So the random number function here is here. We're going to add, oops, 3800 is the oscillator clock counter, and that function is random number. Generate a random number. So if we read that 3800, we should be able to get the value we want. So how do we read that? Well, we're not using the peripheral address register, but we'll push it anyway and pull it after the end just to make a safe function. And basically, instead of loading R8 with 0, we want to load R8 from the peripheral address. So it's load peripheral long from R8 into R8. That'll go and read the PAR, which we have to set first. So let's do a load immediate extended peripheral address register 3800, and we'll load that into R8, and we want to make that a 0 through 255 value, so we'll do an AND immediate of R8 with 0xFF. So that'll give us a value back of 0 through 255, and we're getting that random number up here in this code. So it returns it back in R8. So we could print that out as a long. So let's go ahead and do that. Print long. Go make sure that function does what we want it to do. Basically should non-destructively take what's in D8 and or R8, register 8, not D8, and return that back. So it's pushing R8 and it's pulling it, so it's not destructive, and it'll take and add that value to it. It'll roll it, it'll do one more, so it does 2 digits. That should be exactly what we want. But it'll do it as a long, so I think we're okay with that. Let's go back to where we came from. And here we are. So that'll print out the random number that we got, so we should be able to run it a few times and check and see what it does. So let's go ahead and assemble that. Go through the same process as in the previous video. And we'll initialize memory files, those values. We'll compile it. And we will open up Device Programmer to be ready, because it's going to be pretty quick. And we'll program it. And now let's look and see what that did. Well, it printed out a 41, so that's a pretty good guess. A pretty good way to go. Let's try our 00 and see what that does. Well, that's the wrong number. Try 99. Nope. Well, we know it's 41, so let's see what happens. Hey, we got it. So a random number generator worked fine. Let's try it with a different, reset the card and see what number we get. Came back with 41 again. Doesn't seem likely, but let's try it again. And we'll hit it. It came back with 35. So tried hitting it a few times just to see. 41, 35, 41, 35. Well, a random number generator is only generating 2 numbers, so I wonder what's going on here. Let's go and take a look and see if we can figure out what's going on with the random number generator. Instead of returning back a truncated value, let's leave the full thing just to see what sort of numbers we're getting back out of it. And let's go ahead and compile again. Or assemble. Assembly done. Initialize memory file. Create the FPGA code. Download the FPGA code. And what do we get for a random number now? If we hit COM7, we're seeing 1BC41. And if we reset it, 1BC35, 1BC35, 4D. Ah, we got a different number there in the bottom. 35. We're not quite doing it right. What we've got to do is we're running it from when the program starts, so it will be a very consistent number. We just violated the rule that we were going to do from the very beginning. The random number is being created sometime after the program starts, and it's pretty consistent in time. In fact, the difference between 35 and 41 is probably very consistent amount of time. So what we want to do is create that random number after we do our first guess. So either we move the guess software up, which we could do. We could do that here, and that would work. Or let's think about this for a minute. Probably the easiest way to get it synchronized up to the user starting is we have a function down here called check for character and discard. It's just looking for somebody to hit any key. So if we go home, randomness again will be produced by the user. So before we get the random number, we're going to go and wait for a key. So we will jump off to check for character and discard. We'll just toss away the key. And we want to print up a message saying, hit any key to continue. I think we had one of those hanging around before, but we'll recreate it. Or any key to start, actually, is better. We're not continuing it, we're just starting it. So we want to print out that message, and that will go here. Load immediate long, R8 with that message, and lower. And we want to print that string out to the ANSI UART. And that might do it. Let's see if that works better. Assembled fine. Update memory initialization file. Work fine. You can see if it's immediately here at 40%, we're going to have a quick time to compile it. And we'll start it and download it. And we have a number. Let's see what that number is. We have 2CD7 something. So if I hit it, 2CD89, CDDG. We're still not doing the right thing here because it's a very consistent number. Oops, calling it here. Should be waiting for a character not passing through here. So something's causing it to not wait for a character. That wait for character thing is not really waiting for a character. We probably don't want to call that function. We probably just want to call the get character, and we have several of those. Let's see which one we want. We actually want to wait for a character. That other one doesn't wait for a character. Check for a character and discard. Wait, get character from UART would work, but I think we want something that includes that and the other. Let's see what we have in here for that. Check for character and discard. Let's see what that routine did and why it didn't work. It checked it. Wasn't there. No character was received. It just fell through. All right. Check for a character, discard the character received, and return whether the character is present or not. Okay. So this routine will return, forgot what it did, whether the character was present or not. So what we want to do is wait around while this is 0. So if we check for character here and discard, we can do a compare immediate R8 and 0. Oh, that's not what we want. And branch if it's equal to wait for key hit. All right, that should do it. Forgot what my own routine did. So if we do that, let's see what happens. Now it should come down, should wait for a character. As long as it's still 0, it'll do it. Otherwise, it takes the character and tosses it out, and then it'll call the random number generator. So I think we'll get a better result this time, and I think it won't just pop through at the bottom here. So let's go ahead and assemble that. And go ahead and load the initialization file. That's fine. Tell it to compile the FPGA. We'll now upload it. Check it out. Now it's saying any key to start, so that's good. That's exactly what we want. And it's waiting around. So we hit a key, and it has a number that's 1DF58ED. So a bunch of digits in ED at the bottom. Let's try it again. Just randomly press the button, hit a key. 049. We pressed it a little quicker that time with ED at the bottom again. Press it again. DG at the bottom. Press it again. 4D at the bottom. Actually, I'm seeing the guess there, not the wrong thing. 85 at the bottom. 81 at the bottom. 31 at the bottom. Looks like we've got a nice random number generator. Let's go back and put in the filter here for the 8-bit value. And probably put up here that it returns an 8-bit value. Good enough for what we're doing. Not random if you're up all the way in the digits, because probably the upper bit digits are 0 or 1 depending on how quick you got here. So just picking the bottom bits off should be fine. Let's go ahead. Now we're printing out the number that we got off the random number generator, which is fine, but it's getting a little confusing to see it on the screen. So I think we'll add carriage return line feed in there, which we have up here. We'll copy that. PSR. Before it will print, after it will print, and it stuffs it off at R15. So we should be able to run. It'll give us the number just so we have a hint, so we're not sitting around waiting a long time to guess the number. And we'll get rid of that later to make the program actually a guessing number game instead of a knowing number game. Gotta be careful not to hit that arrow, otherwise it'll take the 2 minutes to compile or start compilation. Update the memory, initialization file, and go. So it's compiling it quickly, as it should. If we wait till it's done, hit upload and look and see what it created. If we hit a key, it gives us a number 5. That could be true. Let's try an 09. Wrong guess. 06. Nope. Let's try the 05. So it does work. It takes the 05 that it got. Let's try it a couple times with different, see what different numbers we get. Hit a key. It's going to get an F5 this time. So we give it an FF. Wrong guess. F5. Right guess. F5. Ooh, we have a logic error here. What's going on? It's showing F5 up here, but this isn't F5 right here. What if we have a logic error in our typing? Ooh, that's interesting too. The uppercase F isn't working. So there's something wrong with our hex routine. We'll have to go debug that and see what's going on. To debug it, let's put the same thing we put in the other routine where we're printing out this long here. Put that same function in here after we get the number back and see what number we think we're getting. That is the hex to 7 segment. We should have that as a value, and it should be returned back in R8. And we probably want to put a new line around it again. And this is what you typed. The first one was the random number, and this is what you typed. So let's see what that gives us for a result. It should hopefully get us a little bit closer to the answer. Symbol. Memory initialization. Yep. Start compilation. I guess they use the word compilation. It's got to be the right word. If they use it in Quartus. And upload it. And let's see what we got now. It's not giving us any key to start. We hit it. So we have a 29. Well, that one's not going to be, but let's try our, oops, that's not going to be a bad number. Let's try 3F. Should get back a 3F. We're not getting back a 3F. We're getting back a DEBD instead of 3F. Interesting. Why is that? If we were putting in 66, what would we get back? Well, we get back 66. So we clearly have a problem with hex digits. 99 works, 11 works, 0 works. Well, it doesn't because it needs 2 digits. 55 works. So we've got something wrong with our hex function. Let's try it with uppers, 6F. Let's try it with lowers. 6F. 6F with lowers did work. So the lowers work. I forgot what the number was that was the right number. The right number is 29. Well, we can get out of here with 29, so we'll do that. Did get it right. Let's reset the card. Hit any key to start. Right number 65. Well, we want to try it with a hex case here. So we'll do it until we get a hex number. Shouldn't be too hard. 35. Let's try it again. E1. So if we do a lowercase e2, well, that does a 2e2. So I think we want to mask the upper bits. That's never going to match. Let's try 2e2, and we'll try e1 just to see what happens. Well, we have the e1 in the bottom, but it came back with the wrong guess. So it looks like we have 2 bugs. One is we need to mask off that hex read value function and get rid of the extra value up there, and the other one is we've got problems with uppercase. Let's try to go figure out what's going on. The masking the result part back is pretty easy. We can just do that here with this. After we get the value back, we just AND immediate R8 and R8 and 0xFF, and that should take care of that problem we saw there. Make sure it works. Always have to assemble, otherwise you just run exactly the same program. Processing, big memory initialization. Now we can do the compile. It's going quickly, 78%, 80, 100. Start it up. See what we get back. It's asking for any key. It wants a 15. Well, this isn't the case that we want, but let's try our 6F this time. And 6F is fine. How about 8F? 8F is returning AF. Interesting. We definitely have something going on here with our code. BF. How about 7F? 7F works. 6F works. So we have a problem here in the code if it's 8, 9, A, B, C, D, E, F in the first digit. Figure out what's going on here. How about FF? Well, that works too. And what was the right number? The right number was 15. Let's see. Yep, got it right. Let's go figure out what's going on with the parts that aren't working. Make sure we know what the bugs are here. Looking for D. If we did a 0D, it gives us back 2D. Interesting. If we do a 2-2, gives us back 2-2. 6-6 is good. DD is FD. So we definitely have a problem going on here. And it looks in this case like it's in the first digit, because the second digit looks okay. Do 0-0, we're good. If we do 7-0, we're good. We do FF, we're good. We do FC, we're good. We do 8-0, we're good. 8-8, good. 8F, it becomes AF. So, interesting. Very interesting. We do AF, we get back AF. So it looks like 8 and 9. 7F looks good. 8F does not look good. 9F does not look good. It seems like we're subtracting something wrong off of here. Our program that goes and gets that number is this function hex to 7 segment. Go and check that out. If you put a colon at the end, it'll go to the actual function. So what's that doing? That looks like it's adding R8 and 0. We could replace that with an immediate if we want. It really doesn't matter. It's the same length if you use register R0, which is aliased here to 0 or not. We're loading peripheral, which is the line buffer. So we're grabbing it off the line buffer. We're taking that and calling a function called ASCII to hex. Then we're ORing that in to R9. The result we get back from that seems like that's probably where the problem is. And we're shifting that left and then taking care of that. So it looks like the ASCII to hex is not working right. And something to do here with the comparison. The comparison values are hard-coded here. 0 through 9 are 30 through 39, A is 41, F is 46, 61, 66 for the lowercase a through F. We got a little bit of a decision tree that happens here depending upon what the value is, and there's clearly something backwards or wrong in here. 3A, looks like if it's less than 3A, or greater than 3A, it's calling got digit. So if 3A is greater than that, or this is less than that, then it calls got digit. And what does got digit do? Got digit subtracts 30 off the number, and that's what it does, which is what it seems like it should do. So where's the bug? Let's take a look at the ASCII chart to get an idea of what's going on here. The numbers that we like are 30 through 39, which are 0 through 9, A through F, which are 41 through 47. That's the uppers, and the lowers are 61 through 67. So how does that compare to what we have up here? Well, F is 66. Sorry, I had the wrong number. 41 through 46 for the lowers, which is right, and 30 through 39 for 0 through 9. Those are the easy ones. You can just subtract off 30 and you got it. But for some reason, even that isn't working. When we do 8 or 9, it doesn't seem to be working. I wonder what's going on. Well, I added a AND of F to the return value from ASCII to hex, and the code seems to be working okay now. Let's try it out with a couple of numbers. Random numbers F5, 77 looks fine, 99 looks fine, 9C looks fine, C9 is C9, and it looks like we fixed that one bug there. 66 looks fine, and the right number was F5, so let's try that, and that works. So it looks like that was the problem, something wrong with the way it's returning a value out of there. Well, we masked it anyway, and the values seem to be right. I don't know if the uppers will work. Let's see that. If that's the case, probably not. Let's try FF. Looking for 91. I have a typo there. I typed it ahead of time. So FF. Uppercases are still not working. Looks like their FF got turned into DD, ED got turned into DD, AA got turned into DD, 4A gets turned into 4D. So there's definitely something wrong. It looks like it's always turning back D in that nibble no matter what for an uppercase letter, so I'll have to go figure that out next. I see the problem here. The problem is the less, this should have been less than rather than greater than, because the comparison sort of operates backwards and we were discarding it. The function returns back DEAD if it's wrong, and that's why we were turning nibbles into Ds. And that should fix it. It was telling us that we typed digits that were wrong, and we were masking it out. Also, it was printing to the screen the syntax error, so it was all there. It was just missing it. So it looks like we got it. We can put in AA and we get back AA, we put in 00, we get 00, put in C5, and that was the number we were looking for. Looks like we got it and it's working fine. So we'll probably, I think we'll stop the video at this point and pick it up in the next video and see how it goes. If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well. We have a store in Tindie where we sell all of our cards. Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.